Hi everyone, it's Mrs. Meehan, and in this lesson, I'll go over about different types of collisions and explosions. So just to kind of reflect back for a moment, we know that there are conservation laws, and they will be involved in the scenarios known as collisions and explosions. So objects in an isolated system can interact with each other in a number of ways. So two key ways in which they interact with each other are collision, so they can move towards each other and collide, or if they start out stuck together, they can explode or push apart. So in an isolated system, it's very important to note that there are measurements that have been done and that we can do that show that both momentum and total energy are conserved. But the energy can change from one form to another. So we've seen this in the past with conservation of energy. When energy is conserved, the total energy of the system is the same before and after. However, it can be in different forms. For example, it can start as potential energy, and some of it or all of it might end up as kinetic energy, but the amounts will be equal. Now, conservation of momentum and change in kinetic energy help us predict what happened or what will happen in one of these events, so collisions and explosions. So we differentiate between collisions and explosions by the way the energy changes or does not change form. So starting with explosions. An explosion is when an object breaks apart because potential energy stored in one or more of the objects is transformed into kinetic energy. So if you picture these objects here, they start out stuck together, and mathematically what you see is that their momentum before, it's the sum of the momentum of A and B. So we have the momentum of A plus the momentum of B. And since they're stuck together, that's equal to the sum of their masses. So their masses are together. So you consider that, you just add them together there, times the velocity. So it's P equals mv. However, you can consider individually the momentum of A plus the momentum of B is equal to mv, but m is the sum of the mass of A and B since they are stuck together. So they are considered one mass in that way. Now, this is before they move apart. So they're moving together here. After the explosion, they are no longer stuck together, but they are now moving apart. They have their individual momenta. So this symbol, the prime symbol, means after. So we have our momentum of object A equals mva, and the momentum of B equals mv of B. Now, there are two types of collisions that we'll be taking a look at, and collisions are when the objects move together and hit. So with an inelastic collision, we have these two objects colliding, and then they stick together. So an inelastic collision is when the objects hit and they stick together. When this happens, they convert some kinetic energy into bonding energy, if these are molecules, heat, and sound. So the energy doesn't disappear, it's just converted to another form. So we have our kinetic energy here as they move together, and then they stick, and some of that energy, it's no longer all kinetic energy, some of that will be converted into bonding energy, heat, and sound. So what it looks like, and you'll notice, I'll show you in a moment, we have our individual momentum in the before for each individual object. So P equals mv for each, A versus B. And then after they collide and stick together, they are now moving together because it's an inelastic collision. And you'll notice that this equation here is the same as the before equation for an explosion. An explosion and an inelastic collision are pretty much opposites of each other when you take a look at that. Explosion, they're together, and then they break apart. Here, they're moving towards each other, they are apart, and then they stick together. So they are opposites. So we see this equation again, where the sum of the momentum of each object would be equal to the sum of the mass of each times the velocity, since they are now moving together as one. Now, the other type of collision we'll be looking at is something called an elastic collision. So this is when two objects collide and they bounce off each other while conserving kinetic energy. So in the previous two examples here, for the explosion and then inelastic collisions, you'll notice that kinetic energy isn't quite conserved. You might have, in this case, some kind of energy transformed into kinetic and then also into other types. And here, some of the kinetic energy is transformed into another type. So with elastic collisions, this is the example where we actually conserve kinetic energy. So they bounce off each other. Here we see before two separate objects moving towards each other, and you can notice that A has a longer vector there. So it's the velocity is a little bit more than B. Then they collide and bounce off each other in opposite directions. And you'll notice the vector lines are intentionally drawn a little bit differently. Now, all of that will still be the same total because energy and momentum are conserved. And you can calculate that using the P equals mv for after. So that prime symbol there is, the momentum of A after and the momentum of B after the elastic collision. Now, this is a very helpful table that kind of summarizes everything here. Now, what we looked at and what we'll mostly be focusing on are these. We have our perfect and elastic collision, which was just described on the last slide. Not the last slide, the middle slide there. We have elastic collisions and explosion. But you'll notice I didn't really talk about general inelastic collisions. Now, technically, in this type, the objects bounce off each other similar to an elastic collision, but some kinetic energy is converted to heat, sound, or energy, to heat or sound energy, etc. So you'll notice here, for an elastic collision, kinetic energy is completely conserved. This is the only case where that is true. Here, you do have objects bouncing off each other. You'll notice for each one, there is a bounce. However, the key difference is that in an elastic collision, kinetic energy is conserved. In a general inelastic collision, kinetic energy is not conserved. Some of it is converted to other forms. Now, another pattern to notice here is that the conservation of momentum is true in each and every case. So in every single scenario, no matter what, momentum is conserved. So really, we're just focusing on these bottom three, but just know there are also general inelastic collision. We'll mostly be looking at perfect inelastic collisions. Okay, let's try a couple practice problems here. So in blank collisions, momentum is conserved. The correct answer is C. So what I just showed you in the table, that for every single case, momentum is conserved, no matter what type of collision or an explosion. In blank collisions, kinetic energy is conserved. The correct answer is A. Only in elastic collisions where the objects bounce off each other, kinetic energy is conserved. That is the only one that had a yes in that column. Now let's take a look at a closer look at conservation of momentum during a collision or an explosion. So we know that measurements can show that the total momentum does not change. Now, how do we do that exactly? So in this case, let's take a look at this collision here. Looks like the two objects are bouncing off of each other. So that would be an elastic collision. So they bounce here. And then they have their individual momenta here. So they have their before, mv for each, and their after. So the mv after. And remember, that little apostrophe or prime symbol just means after, so that you can denote that in your equations. So we know that in this case, what would happen here is that, okay, the momentum of object A plus the momentum of object B would be equal to the momentum after of object A and the momentum after of object B. So in this case, that's what we're going to see. Now, in an explosion, one object or coupled objects break apart into two or more pieces, moving afterwards as separate objects. So in this case, we will assume that the object or a coupled pair of objects breaks into two pieces. That's one thing that we're going to assume here. And then explosion is along the same line as the initial velocity. So it's going to be along the same axis. So it's traveling horizontally, and then the explosion itself will take place. Each object will be moving horizontally apart from each other as well. So we know that before, when they're moving together, that the total momentum of this system will be equal to the sum of their masses, since they are together as one object basically, times the velocity of them together. And afterwards, they're each going to have their own individual momentum here. So the momentum of object A after, so P sub A prime, is equal to M sub A V sub A prime, and then the same thing for object B. Now, what this looks like, when we're talking about conservation principles, we know that the initial momentum here is going to be equal to the final momentum. In this case, we have two objects, so the initial momentum of object A and B equals the sum of the after momentum of object A and B. And up here, since we just said that the sum for the before is equal to M sub A plus M sub B, the sum there of their masses, times velocity, we just sub that in on that side of the equation. And then on this side, they are acting as two separate objects, and when we consider the system here, the momentum of the total system, we have the individual momentum of A added to the individual momentum of B. So when you're calculating this for an explosion, that is the process to get to the correct equation. So take a moment to jot that down if you haven't already. And then just to go back real quick, in this case, it was the sum before plus the sum after for this collision up here. And for the explosion, we end up with this. So the first problem here, a 5 kilogram cannonball is loaded into a 300 kilogram cannon. When the cannon is fired, it recoils at 5 meters per second. What is the cannonball's velocity after the explosion? Okay, so let's see what the givens are here. We know the mass of object 1 and 2, the masses. We know that the velocity of 1 is going to be equal to the velocity of 2. Therefore, we can say the velocity is equal to 0, and that's in the before case. There is no velocity. In the after, we have the velocity of object 2, we'll call that the cannon, since it recoils at 5 meters per second. So our cannon there, that's going to be our object 2 velocity. Now, over here, we have our equation. So we have the before and the after, and that's coming from this slide here, because they are considered a coupled pair, and then they will explode, they will separate. So we will use the equation where in the before, the initial momentum here is, m, the masses of both objects times their velocity is equal to the after. They're acting as two separate objects, so the momentum of object 1 plus the momentum of object 2. Now, we just established that the initial velocity is 0. So that results in this whole side of the equation equaling 0 because velocity is 0, which leaves us with 0 is equal to that. So subtract from each side. So you'll have the momentum of object 1 here equals negative momentum of object 2. What you end up with, you want to solve for the velocity of object 1. So with the cannonball here, we're calling that object 1 since we established that the cannon is going to be object 2. So to solve for object 1 here, that will be equal to the negative m sub 2 v sub 2 divided by the mass of object 1. Putting in the numbers, we have 300 kilograms as the mass of object 2 times the velocity of object 2 after is 5 meters per second divided by the mass of object 1 is 5 kilograms. Gives you the velocity after the explosion for object 1 as negative 300 meters per second. Now the negative symbol means that it is heading in the opposite direction as object 2, which makes sense because if you imagine a cannon being fired, you see that recoil. The ball heads in one direction and the cannon recoils backwards or in the opposite direction as a result. Okay, 2 rail cars, one with a mass of 4,000 kilograms and the other with a mass of 6,000 kilograms, are at rest and stuck together. To separate them, a small explosive is set off between them. The 4,000 kilogram car is measured traveling 6 meters per second. How fast is the 6,000 kilogram car going? Okay, so we have our givens listed here. We want to figure out how fast the 6,000 kilogram car is going, and we will call that object 1. So the 6,000 kilogram car, that will be object 1. We want to figure out the velocity 1 after. So I'll put the prime symbol there. So we want to figure out, or what we know so far is that object 1 is 6,000 kilograms, and then object 2 is 4,000 kilograms. Now the velocity before is going to be 0. They are at rest and they are stuck together. Since this is the case, this is going to be an explosion. So to separate them, a small explosive is set off. We know this. The 4,000 kilogram car here, is object 2, is measured traveling 6 meters per second. So what is the after velocity of object 1? Using the equation here, we have our the total of the masses of both objects since they're stuck together times the velocity. The velocity is 0, so that side of the equation becomes 0. That is equal to the momentum after of object 1 plus the momentum after of object 2. Subtract from both sides, so we have what we end up with is the momentum of object 1 after is equal to the negative momentum of object 2, and that makes sense since after an explosion, we're assuming they will be moving in opposite directions to each other. So we have, solving for velocity, we divide by the mass of 1 on both sides. Putting in the numbers, what we end up with is negative 4 meters per second as the velocity for rail car 1. Okay, so let's take a look at perfectly inelastic collisions. So there are inelastic collisions, and we're just mainly focusing on the perfectly inelastic collisions where one object hits another and then they stick together and move as one. So recall that this is basically the opposite of an explosion. So with an explosion, the two objects move apart and then act separately. And you'll notice the equation is this. Since a perfectly inelastic collision is the opposite of an explosion, we're using the same equation, it's just written in the opposite way. So we have our momentum before and our momentum after for the system before and after. With the perfectly inelastic collision, they are traveling separately at first. So it is MAVA plus MBVB added together. And that the sum of that would be equal to the MA plus MB here. Since both masses are now stuck together, you would just find the sum. And they are moving together at a certain velocity, so multiplied by that velocity. This is the key equation that we use to solve problems for perfectly inelastic collisions, and it's just the opposite of the one for explosions. So let's try out a few practice problems to wrap up here. So at 13,500 kilograms, a railroad freight car travels on a level track at a speed of 4.5 meters per second. It collides and couples, or attaches to, with a 25,000 kilogram second car, initially at rest and with brakes released. No external force acts on the system. That means we're assuming a constant velocity here, so no acceleration. What is the speed of the two cars after colliding? Okay, so we have all of our givens listed here. What we want to find is the speed of the two cars after the collision. So we have the masses and velocities initial for both cars. We have the velocity after here. So taking a look at the equation, fully written out and derived, we have our sum here of the two objects separately. Now object 2, the velocity is 0, so you'll notice that becomes 0. Let me get my pen here. So you end up with m1v1 plus 0 is equal to, and since this is a perfectly inelastic collision, the masses basically act as one, they are stuck together, times the velocity. We want to find this velocity of both objects stuck together after. So you want to divide by m1 plus m2 on both sides. Plug in the numbers, and that gives you 1.6 meters per second, and that would be in the same direction as the first car's initial velocity, since this is a positive number. If it was a negative number, it would indicate that it would be moving in the opposite of the initial direction. A cannonball with a mass of 100 kilograms flies in horizontal direction with a speed of 800 meters per second and strikes a ship initially at rest. The mass of the ship is 15,000 kilograms. Find the speed of the ship after the ball becomes embedded in it. Okay, so we have our givens listed here. So the cannonball is object 1, the ship is object 2. We have masses and velocities for each. And again, we want to find the speed of the ship and the ball together, both objects together. So the after velocity. So again, object 2 is at rest, which is the ship. So that ends up being 0. Add that to the total momentum, to the momentum of object 1, and that would be equal to the after momentum of the system. Rearrange, divide by m1 plus m2 on both sides to solve for velocity after, and you end up with 5.3 meters per second in the same direction as the cannonball's initial velocity. A 40-kilogram girl skates at 5.5 meters per second on ice toward her 70-kilogram friend, who is standing still with open arms. As they collide and hold each other, what is the speed of the couple? So we have our givens, and we're finding the speed of the couple here, so both objects together after the collision. So same exact derivation as the first two problems, solving for the after velocity and plugging in all the givens, you end up with 2 meters per second, which is A, and that would be in the same direction as the 40 kilogram girl's initial velocity. Now, some of the practice problems that go along with this lesson, which can be found on Google Classroom, are chapter problems 35 to 65 and multiple choice 11 to 20. Some of those might include problems for elastic collisions, which we have not gone over yet, but were just mentioned in this lesson. So you can hold off on completing the elastic collision problems for now, unless you really want to give them a try.